This is the second lesson in our gas chemistry unit. In the first lesson, we were looking at the relationship between temperature, velocity, and diffusion rates using Graham's law and the kinetic molecular theory. This lesson will continue to use the kinetic molecular theory in an effort to help us explain why gases exert pressure. And so because of that, we will be looking at Dalton's law of partial pressures for gases. So gas pressure. In order to understand gas pressure, we just want to get a sense of what pressure is to start with. Any pressure, whether it's being exerted by a gas or anything else, is simply a force per unit area. The symbol that we often use for pressure is the capital letter P. Another way of looking at pressure, as far as a definition, would be an equation. Pressure would equal a force applied divided by the area over which that force is applied. If we have a gas in a closed container, or not necessarily a closed container, a gas period, it will exert pressure on its container by colliding with that container. As we know, particles of gas are continually moving around. They're going to run into each other. They will also strike the container that they are in. Every collision between a gas particle and a container applies a force to that container. Now, each individual collision applies very little force. We're talking about tiny, tiny, tiny particles here. So an individual collision applies almost no force. However, if we're talking about any reasonable sample of a gas, we have a huge number of particles. So that huge number of particles will result in lots and lots and lots of simultaneous collisions. In other words, there are enough collisions to build up or to produce a substantial force. If we're talking about atmospheric pressure or air pressure, we're simply talking about the pressure that's exerted by the gas particles that compose our atmosphere, which is mostly nitrogen and oxygen. In fact, that accounts for over 99% of our atmosphere. You also have some carbon dioxide and some water vapor and some argon and some other gases, but mostly nitrogen and oxygen. This atmospheric pressure will vary by location and altitude. If we go to a different place on Earth or we change our altitude, the atmospheric pressure will change. Atmospheric pressure was first measured by an Italian scientist by the name of Evangelista Torricelli. And our next slide here has a picture of a basic device that would have been similar to what Torricelli would have used for determining atmospheric pressure. How it works is really quite simple. We have a tube, probably made of some sort of glass, and in that tube at the top there's a vacuum. There's nothing there. There's no air there. There's nothing at that end of the tube. And that tube is submerged in a pool of mercury. That's what this gray stuff is. So this is liquid mercury here. And when you submerge it in that mercury and then turn it upside down, so this end down here would be open, you turn it upside down, atmospheric pressure, or particles that make up the air, are pushing on this pool of mercury that sits in this some sort of bowl or dish that we have here. And that force from the particles that make up the air, it's going to push that liquid mercury up the tube. Well, as you can see based on the diagram, that it's pushing it to a height of almost 30 inches, which is 76 centimeters, or that would be 760 millimeters. So when you see the unit millimeters of mercury, what it's referring to is a gas pressure or a pressure period, typically gas pressure, and it's talking about how high the gas could support a column of mercury. If we are at standard atmospheric pressure will support a column of mercury 760 millimeters high. That's what we're showing here. 76 centimeters would be 760 millimeters. So we would say here that the atmospheric pressure is 760 millimeters of mercury. There are lots of different units of pressure. The base SI unit for pressure would be known as the Pascal, named after a physicist by the name of Pascal. And you can see the symbol for the Pascal there is capital P lowercase a. And breaking that down into something that's a little more familiar to us, a Pascal is a Newton per meter squared. Remember, Newton is a unit of force. Meters squared would be a unit of area. So 1 Newton applied over an area of 1 meter squared, that would be a Pascal. We really don't use this unit hardly at all because it's such a small unit of pressure. 1 Newton is not very much force. Applied over a large area of 1 meter squared, that's going to be a very small pressure. So to put this in perspective for pressure units that we do use more often, let's just look at the values of standard atmospheric pressure with some different units. Here are various values of standard atmospheric pressure using different units of pressure. This first one here, notice it's pascals, but it's actually kilopascals, kPa. Standard atmospheric pressure in kilopascals is just over 100. As you can see here, 101.325 kilopascals. So we need 101 kilopascals to get to standard atmospheric pressure. In pascals, that'd be over 100,000. So you can see what a small unit of pressure 1 pascal is. That is the same thing as 1 atmosphere. 1 atmosphere, that would be the definition of 1 standard atmospheric pressure, which is also the same as we saw in the last slide of 760 millimeters of mercury. These first 3 we will use most commonly, and these I will ask that you know, or that you memorize these. It won't take you much work to memorize them because we'll use them quite often, but these 3 we use a lot, so I'll ask that you memorize those values. There are a couple others I put on here just because we do see them from time to time. This next to last one here is the torr, named after Torricelli, and you'll notice it's actually the exact same thing as a millimeter of mercury. So if you ever see that pressure unit, the torr, that's exactly the same as a millimeter of mercury. And then one that we might be most familiar with, because we see it most often in our everyday experiences, would be pounds per square inch, which might not be written as you see it here. We might be more familiar with it written as PSI, but regardless, it's still pounds per square inch, and that is a standard atmospheric pressure is just under 15 pounds per square inch. So in order to help you get familiar with these units, especially these ones that you need to memorize, I'd like you to perform each of these conversions here. I'll do the first one here as an example, and then please pause the video and try to do the other 2 on your own and see if you got them right. Alright, so this first one here, we're asked to convert 87.9 kilopascals into millimeters of mercury. So this is just some basic dimensional analysis. We're looking for our pressure in millimeters of mercury. We're given a pressure in kilopascals, and so I just need to look at my equality up here and ask myself, what is the relationship between kilopascals and millimeters of mercury? And we can see very clearly that 760 millimeters of mercury is the same as 101.325 kilopascals, so that's my conversion factor. Note my units go where they will cancel, kilopascals in the denominator of my fraction, cancel with the kilopascals we're starting with, so they cancel, and we're left with millimeters of mercury, which should give you 659 millimeters of mercury. So go ahead and pause the video, try those next 2, and then play it, make sure that you got them right. Alright, these next 2, I'll just quickly put them up here so you can check them out. You can see going from 1.35 atmospheres to kPa or kilopascals should give you 137 kilopascals, and then going from 98 millimeters of mercury to atmospheres should give you 0.13 atmospheres. The goal is, with these, obviously we want to be able to do the conversions, but basically we want to be able to look at a pressure value, whether it be in kilopascals or atmospheres or millimeters of mercury, and we want to compare that to what we know for standard atmospheric pressure. So for example, if we were to see this value here, 0.13 atmospheres, we should be able to look at that and say, well, that's significantly less than standard atmospheric pressure, because we know that standard atmospheric pressure is 1 atmosphere. Or we look at this middle one here, 137 kilopascals, and say, well, it's a little more than standard atmospheric pressure, because we know that's about 100, or 101.325 kPa, as we can see here. All right, last topic here for this lesson is on Dalton's law of partial pressures. Here is a statement of Dalton's law. It says that the total pressure of a mixture of gases equals the sum of the pressures of all the gases in the mixture. A word you might not be familiar with, or a phrase that we need to look at that will help us out here, is the phrase partial pressure. When we see that phrase, all that means is that is the pressure that's exerted by a single gas in a mixture of gases. So if I have a mixture of two gases, say nitrogen and oxygen, and actually I have a picture up here that will help us with that in just a second. If I have a picture, I have a mixture of nitrogen and oxygen gases, those two gases together are going to exert some total pressure. The pressure just exerted by the nitrogen would be the partial pressure of the nitrogen. The pressure that's exerted just by the oxygen would be the partial pressure of the oxygen. So in mathematical terms, we could write Dalton's law like this, where we could say the total pressure by a mixture of gases is the sum of the partial pressures, where P1, 2, and 3 are partial pressures of gases 1, 2, and 3, and we just add them all up. So if there are 10 gases, we'd add up all 10 gases, all their partial pressures, to get the total pressure. So here's that picture I was referring to here, where we have a mixture of oxygen and nitrogen. I'd like you to focus on this last picture here. So if we were to measure the pressure, the gas pressure exerted by that sample, we would see this, 752 millimeters of mercury. There's no way that we could just read the pressure of the oxygen or the nitrogen if they're both in there together. But what the partial pressure is, essentially, is if we were to take all the nitrogen out, so you see all those yellow molecules there, if we were to take all the yellow nitrogen molecules out and be left with just the oxygen, it would exert this pressure, 159 millimeters of mercury. If we were to take all the blue oxygen out and be left with just the yellow nitrogen, it exert a pressure of 593 millimeters of mercury. And you'll notice if you add those two together, 159 plus 593, you're going to get the total pressure of 752 millimeters of mercury. So let's look at an example here of how we would use Dalton's law. So here's the problem. A mixture containing oxygen, carbon dioxide, and nitrogen has a total pressure of 0.97 atmospheres. So just start visualizing this. We have three gases in this mixture. We have oxygen, we have carbon dioxide, we have nitrogen. When we measure the pressure of that mixture, the pressure is 0.97 atmospheres. Remember, that's the total pressure. So here's the question. What is the partial pressure of oxygen, of O2, if the partial pressure of the CO2 is 0.70 atmospheres and the partial pressure of the nitrogen is 0.12 atmospheres? So based on Dalton's law, we know that the total pressure here is going to equal the sum of all the partial pressures of those three gases. So it would be equal to the partial pressure of the nitrogen plus the partial pressure of the carbon dioxide plus the partial pressure of the oxygen. In this question, we're asked to find the partial pressure of the oxygen. So I'm going to solve this equation for the partial pressure of the oxygen. Notice the symbol there, P and the O2. So I'm going to subtract the partial pressure of the nitrogen from both sides. I'm also going to subtract the partial pressure of the carbon dioxide from both sides. So they'll cancel over here on the right side, and I'll just move them to the other side. So that gives me the partial pressure of the oxygen equals the total pressure minus the partial pressure of the nitrogen minus the partial pressure of the CO2. So at this point, it's just a matter of substituting in the values we're given. We're told the total pressure is 0.97 atmospheres, and then subtracting the two partial pressures, the 0.12 atmospheres for the nitrogen, the 0.70 atmospheres for the carbon dioxide, we will get our partial pressure of oxygen of 0.15 atmospheres. One thing to note here is this particular problem, we didn't have to worry about it, but these pressure units could be different. In this case, all the units of pressure were given were in atmospheres. But if we were given, say, one pressure in atmospheres, another in kilopascals, another in millimeters of mercury, if we are to apply this equation, whether we're adding or subtracting, as we know, when we add or subtract, our units have to be the same. So just be cognizant of that we're not just looking at the numbers. Pay close attention to your units, as we always want to, in order to make sure that you are doing it correctly. All right, this ends this lesson on our gas chemistry. So just reviewing the learning targets here, we continued to use the kinetic molecular theory today, talking about the motion of gases and how they produce gas pressure. And specifically, we're looking at Dalton's law of partial pressures to relate partial pressures in a mixture of gases to the total pressure.